Okay, so we have recording in progress, and let me pull up today's class. So we were on chapter 3. Oh, so I have an announcement to make. I was looking at my class size, and I'm thinking, wow, I've got a really small class here. I can afford to do something I rarely do. What we're going to have is you guys can, after you take a test or a quiz, if you come to my office hour shortly after that and can explain to me in person everything that you got wrong and get it right, I'll give you half credit for the stuff you missed. Um, Now, I've had mixed results with this. I've had people who can't ever explain things to me, no matter how many times I give them a chance. So just make sure you can do it. Make sure you really understand it, and that should help avoid problematic grades. I would do this all the time, but I get 100 students and it's just not scalable. Okay. Um, the next thing is I have to actually have an office hour. So let's take a minute to try and figure that out. Um, so let's see, today is here. So what I would like to do is how many people have, say, 3 to 4 on Tuesday? Works for them. Nobody. I'm sorry. Why do I not have the class in here? Okay, let's say 1 to 2 on Tuesday. Who can do that? Yeah, so I mean, if you can just sort of make half of it, that's at least part way. What about that same time, 1 to 2? What about that time on Thursday? Yeah, all right. Okay. What about Wednesday, 3 to 4? You can't do that one. Wednesday, 2 to 3. No. Wednesday, 1 to 2. Uh, Wednesday, 12 to 1. 12 to 1. Well, I mean, are you available at any time, Brian? If you're not available at any time, then I just won't worry about you. Are you literally not available at any time? No, no. Okay, let's go back and try Wednesday, 3 to 4. Yes, 2 to 3, 2 to 3. Okay, Wednesday 2 to 3 will be the time. All right, all right. And so I'm going to have this policy where you can come to me and try to explain the things you got wrong. You have to make sure you understand it though before you come to my office. Don't just come to my office and wing it without looking anything up. I've had that happen. Okay, Wednesday 2 to 3. I should mark this. Yes. Uh, just reasonably soon. The next office hour, 1 or 2 office hours at most. I'm gonna put office hour here. What's your name again? Kendrick. Okay. I'll put this in here now so I don't forget it, which, is not really a guarantee either, but uh okay. All right. All right, that's out of the way. Let's go to chapter 3, which is where we were. And any questions on anything in particular in chapter 3 that we've covered so far? Yes. It's completely different. Pipelining is a form of parallelism where you have a bunch of different workers each doing different things. Linearizability is about a way to check the consistency of the way your code works in memory. So, yes. Hmm. Okay, let's go to that one. Um, the problem is, in order, you have to be able to DQY, right? That's this one up here. But there is nothing in here that is DQing X, and X isn't queued, and this is a FIFO. Yes, queues are FIFOs. So it's queues are always FIFOs, stacks are LIFOs. Remember? So you have to get the X out before you can get the Y out is the issue. Okay, now I have to catch up on the participation thing to make sure I get that recorded. Today's the 9th, right? Sup 9. All right. Okay. So I'll just start from here and we'll take this example. So this example is linearizable, right? Because I can pick those two locations and it will work, right? And then I've got this one. I should do slide show mode. All right. So this one, is it linearizable? Ryan, why isn't it? Okay. So the first question is, which gets in queued first, the X or the Y? But I can choose the linearization point. So I can have either one in queue first. Okay. And I can have either one DQ first. So there's multiple orders that work. Um, so multiple orders are okay. That still fits with our notion of linearizable. And then we had this one. Was this one linearizable? No, because at this point, when I have read one, by the end of this arrow, this right one had to have already happened. And there's no way I'm going to get a 0, right? Make sense? Okay, how about this one? Yes, right? We can definitely make that work. Okay, and so now we have some notation that they want to. I'm not. I think the notation is kind of useful in that it's sort of what if you were logging this from a program, this is probably what the kind of thing you would create for yourself. So we're going to say thread A, enqueues object Q with arguments X, right? And so we look at the history of something. We have thread A and Q's 3 and then the NQ returns and then NQ's 5, and that isn't on here. That we just didn't capture that in this time interval. And then on thread B, we NQ4, we get that back. We DQ3, we get that back. Okay. That's a sequence of events that we observed. Um, eh, well, they're overlapping, right? So the 3 starts here and ends way down there, right? And the NQ5, we never see the 5 again. We never see it return or anything. And then the NQ4, we do see return, right? Um, and I'm sorry, Q.DQ, yeah, it gets the 3 back. I'm sorry, this is the NQ and this is the DQ. This is the right. Okay, so they're not overlapping really, but in any event, you have threads. So these have the same threads. These have the same objects. And here's just another execution. NQ3 return, NQ4 return, DQ3 return, right? And you could say the history for this object Q is that, or you could have the history of thread B is that, right? Because there's a Q and a P here. And so you can have, those two match, those two match, those two match. And that's a final pending invocation that doesn't finish. Okay, so in this case, the methods don't interleave. And here's another execution. And here we're going to take the execution on the history on thread B and the history on thread A, and they look like this if you look at them separately. And you can have what's called an equivalent history if you have some different sequence of events that gives this same result. So the threads see the same things, right? And this is kind of similar to linearizability if you can find these equivalent things. So this one, these things are interleaved, and this one they're not, right? So that's kind of what we're doing when we're picking linearization points, is we're translating from H to G. We're finding an equivalent history where things are distinct. A sequential multi-object history H is legal if for every object X, H of X is in the sequential specification for X. So, right, and so if this is a Q, then the FIFO, it has to come out in the first in, first out order. And if it's a memory location, the last thing written has to be the thing that you read. A method call precedes another if the response event precedes the invocation event. So we can say that one method call, like so Q NQ3 precedes the DQ of 3 because the response precedes the invocation. And non-precedence, we've got these two overlap, and so they have non-precedence. And so we have the notation here. We have a history H and method executions M0 and M1 like this in H, and we say that M0 precedes M1 if M0. We say that M arrow 1 if M0 precedes 1, and the relation M arrow is a partial order, and it's a total order if H is sequential, right? If we just had a single thread, it would be a total order. And a history H is linearizable if it can be extended to G by appending 0 or more responses to pending invocations and discarding other pending invocations, so that G is equivalent to a legal sequential history S, where G is a subset of S. So the idea is, it's basically the same thing as drawing these lines. So if I have G and I have this AC and BC like this, then I can make this work, right? So I thought this was the one with the missing. Oh yeah, there's pending invocation here, right? So if we need to complete C, we can, and we can say that B precedes C, but we didn't get that in our original history. Okay, so some pending of indefect, some of the yes, Matthew. It's not Matthew. Who are you? Baron. Shoot, it's not a bad name, but I thought, uh, darn it, who is Matthew here? Okay, Matthew is not here. Sorry, Baron. Okay, you're lost. So let's back up. Um, so okay, so the idea that NQ, this means something, an NQ method starts, makes sense, right? Yeah, the object queue has the NQ method has been called with a three, but we don't have a response to it, right? It's just going on forever. Well, it means in the time that we've looked at, we didn't see the response come back. So we're looking at a window of time. We're looking at what the computer is doing during a window of time. And we did not see the NQ method come back. That's right. We just didn't see it return. Okay. It started processing, and maybe sometime in the future after this period, this window that we're looking at, maybe it does complete, but we didn't see that. And then here we're in queuing four, and we do see the return. Okay. Here we're dequeuing four, and we do see the return. Okay. And then we're NQing six. So because we NQ'd four and DQ'd four, that means that the NQ3 hasn't happened yet, right? It hasn't happened yet at this point. And maybe that thread is stuck. Maybe something happened to it and it's never coming back, right? Or maybe it's coming back in a minute or so. But in any event, when we're constructing when we're trying to figure out linearizability and so forth, we can just disregard it because nothing really depends on it. Like if something had DQ'd a three, then we couldn't discard it, right? Because we need to see that. Okay. Um, and you understand start and stop, right? Hmm. The Q is a FIFO. So I put in a three, I put in a four, and then I go to pull something out, I get a three. And I go to pull something out, I get a four. And what we're doing when we write this, yeah, when we're DQing, we get a four. You can't DQ a specific number, but yeah, okay. So I can see why this is confusing because we did that we had notation like that somewhere, didn't? Okay. All right. Okay. There is a video, right? There are videos. So you can watch those if you're sick. You do know that, right? Yes. Okay. Um, uh, so here's an example, right? We can complete that pending invocation if we want to by putting a void there. I think we could, and we can discard the NQ6 because, we don't ever do it. But those are the choices we can make. And now we have a history like this, and we can write an equivalent history that looks like this, right? So each thread has, if I take the history of B and the history of A, I see the same thing, but this one is sequential, right? And this process of doing things textually is kind of like what we do with drawing the lines, except far less intuitive. McKay, yeah. Yeah, right. If we were to DQ a six somewhere, then we would absolutely have to keep it. Hold on. Let me back up and let me hear your question again. Right. It's an NQ6, right? It does not return. We can discard it. If the return was there, no, we wouldn't discard it. Okay, so what we're doing, right? Hold on. So no, what we want to do, right? here is the list of events that we saw on our log file, say. Now, what we want to do is we want to construct an alternate version of events, right? Such that if I say h of A on each of these, I get the same thing. And h of B on each of these, I get the same thing, right? So if I look at this h of A, I just have these two events in this order, and that's what I get here too. And if I look at h of B, I just get these four events or these four events, and they're the same order, right? So it's the same. That's what we're looking for. It's equivalent sequential history. And the history is linearizable if and only if for every object x, h of x, the object is linearizable. So we want, for linearizability, we want to linearize on the objects. So this is a linearization, but I think from now on, and for like homework and so forth, I'm going to focus on the graphical version because it's much easier to understand. All right, so linearizable is a nice tool for us to understand whether objects are behaving correctly and whether we can reason about them in a sequential manner, right? So we want to be able to do that. We want to so the idea is this is a specification tool for shared objects, and it allows us to capture the notion of objects being atomic. You know, they're in one state, then they're in another state. And the advice is don't leave home without it. Alternatively, we have what's called a sequential history, sequential consistency. And this time we don't have to have a subset because we're gonna do something tricky. We don't need to preserve the real-time order of events for declaring whether something is sequentially consistent. We cannot reorder operations done by the same thread, but we can reorder non-overlapping operations done by different threads. And this is often used to describe multiprocessor architectures. So here's an example. We have an NQX and a DQY, and we have an NQY, right? And you know, so we can say NQX and DQY, and this obviously doesn't work, right? So it's not linearizable, but it is sequentially consistent. So when I do sequential consistency, wait a minute. Oh yes, okay. So if I want to do sequential consistency, the way I think about it, right, is you can slide methods, these method calls along the timeline that they're on, along their thread timeline. But you can't slide ones that are on the same line past each other. So I can't move this NQX to the other side of the DQY. What I can do, right, is I can slide this NQY way over to the left here in front of the NQX. And so now that's consistent, right? If I can slide that over here, then I can make this all make sense. You with me? You're not with me? Yeah, so I'm allowed to slide these things like they're beads on the string, right? But I can't slide them through each other. So NQX and DQY, NQX precedes DQY. There's nothing I can do about that. But I can push the time of NQY way over here. And now NQY happens before NQX, and when I DQY, it all makes sense. Reagan gets it. We're trying to determine whether the execution is sequentially consistent. Okay, this is a type of consistency which people use to analyze parallel programs. Barron. The question, it does. It has to be. But, right. So the idea is we want to be able to say that the user is allowed to reason about their programs and with sequential consistency. And the computer has the freedom to reorder operations, say, in the same thread. Um, so like an example is, let's say I have a code that says, if A, x equals 5, else x equals 3. Well, the compiler might write x equal 3 if A, x equal 5. And then when I go to observe those things by another thread, I might see the 3 before I see the 5. I mean, the point is the compiler can reorder things so long as it thinks its thread is sequential. And it can do that kind of thing to optimize, right? It'll switch operations around and so forth because it thinks you can't tell, right? And so if you want to maintain sequential consistency, that limits, if you were to maintain, if you were saying this is sequentially consistent, it says this is the limit that you have, and when you're reordering stuff and messing around, is you have to keep this for the programmer. Okay. Make sense? We'll find out. Right. You can slide them around for sequential consistency. All right. Somebody was trying to call me. I hope it wasn't important. Okay, so sequential consistency is not a local property, and so we lose composability. You remember composability, right? We talked about that with locks. We talked about composability with locks. We said you don't programming with locks is not composable. And we said that if you look at one piece of code, you can't tell whether the application is going to deadlock. You have to look at sort of the whole thing, right? And a similar thing happens with sequential consistency. We can't just look at one object. And we get this wonderful property. H of P is sequentially consistent. So for the P object, and for the Q object, right, it's like this. But the ordering imposed by P is like this, and the ordering imposed by Q is like this, and they don't mesh, right? And so you have this closed time-like curve if you want to keep it all consistent. And some people will say that computers, that in some of these computers, that time travel happens. Um, but in any event, you can't, when you combine the objects, it might not work, right? You might get a mess like this. Uh, okay. And so that's sequentially consistent. So you know how to take something that's linearizable and identify it, right? If I give you an execution, and if I give you an execution, you can also tell me whether it's sequentially consistent, right? Okay, well, what about this execution here? Is it linearizable? No, it is not. Yeah, there's no way I'm going to get there. How about sequentially consistent? Can I get it to do that? No. We have quiescent consistency that allows a group of overlapping calls to be reordered. So they cannot be reordered across a quiet region, that is, a blank spot, right? But these things are a group of overlapping calls, and so I can reorder them. So this is quiescently consistent. So what about this execution? Is it linearizable? Is it sequentially consistent? Yes. Is it quiescently consistent? Yes. Kendrick. Okay, so remember, the rule is I can slide things around like beads on a string, right? So if I slide this right 2 over to the left, and I slide this right 3 over to the right, and I get a write before a read. So the execution becomes write 2, write 1, read 1, write 3. So that's sequentially consistent. The last one, um, I can slide things around all day long, but this write and read are on the same thread, so I can't reorder them. That's actually the only difference between these two executions, right? I just moved the read. Okay. Uh, what is this? Is it sequentially consistent? Is it quiescently consistent? No, right? So we've seen something that has both sequential and quiescence. We've seen something that's sequential by itself, and we've seen something that's quiescent by itself, right? Yes, Ryan. Yeah, the idea is if you have a group of overlapping things, you can reorder them. Just the overlapping ones. So the 2 and 3 here could be reordered, but that doesn't help you. Okay, what about this one? Is it linearizable? Uh, is it linearizable? Yes, it is. Yes. Right. So, okay. Yes. You put a line here and a line here, and you've got it linearized, right? Because the order becomes write 2, write 3, write 1, read 1. Is it? Yeah. The operation does take the entire length of time to complete, but the question is, when is the change visible? Yeah. Yeah. So it's when does the change become visible to the program, and can you find a way to make it make sense? Um, is it sequentially consistent? Yes. Is it quiescently consistent? So this is all three. But so is there an overlap between these things? We know that something can be just quiescently consistent or something can be just quiescently consistent. But if it's linearizable, then it's automatically sequentially consistent and automatically quiescently consistent because linearizable is like a subset of those things, right? It's more restrictive than any of them. So if you've got linearizable, you've automatically got the other two. All right. Real world hardware memory is weaker than sequential consistency, but you can get consistency at a price. And becomes very tricky stuff when you go into the details of parallelization. We're gonna, see some of the trickiness. We've already seen a little bit in the need to use the atomic arrays with the filter lock. But linearizability is more appropriate for high level software and analysis. So you want to make sure that you get something that you can reason about at the end of the day, and that's why we go through these consistency analyses. Okay, so you've seen progress conditions, you've seen deadlock free, and you've seen starvation free. Anybody remember what deadlock free is? What Calvin? Right, right. I just wanted to give him a chance to. He hasn't spoken yet this class. All right. Yes, it's when some through all there's always the system is always able to make progress, right? What about starvation free? Right. All of the threads make progress. Now we have two more things. We have lock free and wait free. So here's a repetition of the deadlock free. And if some thread calls lock and never acquires the lock, then other threads must complete lock and unlock calls infinitely often. And the system as a whole makes progress even if individuals starve. And starvation-free says if some thread calls lock, it will eventually acquire the lock, and individual threads will make progress. Lock-free says infinitely often some method completes in a finite number of steps, and the system as a whole makes progress even if individuals starve. So this might not make a lot of sense to you right now because you're thinking, why wouldn't another thread make progress if there's no, uh, why wouldn't it make progress even if there's no locking going on? Yes, I know technically what you're saying. The question doesn't make sense. Starvation is something that applies to blocking, but yes, the point is something can be can have no locks in it, but still there can be threads that can't make progress, and we'll talk about why that happens, how that happens. Okay. All right. And then there's wait free, which says infinitely often some method completes in a finite number of steps, and individual threads make progress. So those are the four conditions. And we have a little table here. We have blocking and we have non-blocking. One thread makes progress or all threads make progress. And so it looks like this. All right. And in order to really make sense out of this, you kind of have to know what what it, a little bit about atomics. So you can imagine that using locks, I create a special wrapper for an int, and they call it an atomic int. And what I'm going to do is I'm going to create this reentrant lock, and it's going to have this volatile int value in it. And I can either, let it initialize to 0 or give it a specific value. I have a get method, I have a set method, and I have a get and increment method. So I can do lock.lock and return value plus plus and unlock, right? And this is all pretty simple and it should all work. And it can't deadlock, right? Because there's clearly no way that it can compete with any other lock, right? It's got its own private lock. It doesn't share. It doesn't try to get any locks inside its methods. So therefore the use of it will be composable. And there's a hardware implementation of this class that exists that it doesn't use locks. Are you raising your hand? And get and increment can be wait free, right? It can be like a single instruction. And we'll learn a lot more about that later. All right. And so here's a code that uses the atomic int, right? And each thread is going to be wait free. It's going to call this increment and get, and it's going to do it n times, and it's just going to complete in n steps. But this, but even though that is wait free, uh, the main thread, which is waiting for all these threads to complete, is not wait free because it's got a loop and it can go infinite number of steps potentially before it's done. Right. So what's going on here is you can call thread.activeCount, right? And that'll give you the number of threads that are still running. And if there are two, that means that there's something running in addition to the main thread. And if it's one, it's only the main thread. So if it's greater than two, then something is still running. And then we can call thread.yield while we wait. Okay. So this is lock free, and the other is an example of wait free. And then there's this unfortunate thing that happens. So this is the way the atomic integer is implemented inside the Java source code. Instead of calling the instruction for atomic increment, it calls compare and set. Now, what compare and set does is it checks to see if the value of the atomic integer is equal to this current value. And if it's not, then this returns false. And if it is, then it changes it to the next value and returns true. And this, because it's in a loop like this, can't be wait free, right? Because there could be other threads that come in and they keep calling that increment thing at the wrong time, and the compare and set can always fail, right? So even though theoretically when I'm calling get and increment, I should have a wait free method. The way it's implemented in the Java platform, I get a lock free method. Oh well. Any questions about any of that? Yes, parent. Yes. So the concept is this table, right? We have blocking methods, and those are things that are getting locks, right? They're either implementations of locks or methods that use locks. And if they're deadlock free, that means that the system is guaranteed to make progress, right? Maybe some individual thread gets stuck, but the system as a whole continues to make progress. All the other threads can keep working. The other one just keeps waiting for its lock and it just doesn't get its fair turn. Starvation free means that all the threads are guaranteed to make progress. Okay. Um, but the fundamental difference between lock free and deadlock free is blocking versus non-blocking. So if I'm using, say, these atomic instructions, and I'm in a loop while I'm waiting, or if I'm spinning on waiting for all the threads to finish, right? Then I'm lock free. I can't say I can't pick some finite number of steps and say that's when the method completes, right? Even if it's a billion, I can't say. It might be more than a billion. Whereas wait free, I can identify a finite number of steps that the thread can take and it will be done. So if I go and I look at this code here, right? This is one instruction and I'm doing it n times, guaranteed to be wait free, right? Provided, of course, it would be if this were implemented the way you'd expect. So this would be wait free because it's n times one, whatever, if you want to think about it that way. Whereas, right, this has got a while loop in it, and a while loop generally means I'm waiting for something to happen. And if I'm waiting for something to happen, I can't guarantee anything about the number of steps it's going to take. Does this all make sense? Piece by piece. All right. Okay. All right. And I guess that's everything I have on 3. Um, I wanted to show you. No, I didn't add anything to 2. I thought maybe I had. All right. So I wanted to show you something I did chapter 1. I thought of something else I wanted to show you there. So you may recall that uh, we had Amdahl's law, right? Remember this? It was on your quiz. All right. We had Amdahl's law and we had, examples of how the speed up calculation worked, right? And then we had a graph, and then we had Gustafson's law, and we had a graph for that. But here is here is another one, and this one isn't widely known because it's from a paper that I was on recently, but it just shows you how you can apply the basic materials of this class. And it was because, I've taught this class that I knew how to do this, right? So suppose you have an array operation that you want to parallelize. I want to compute Fibonacci numbers on an array of a million that's a million things long, right? Or something. And I'm going to divide it up into n pieces. And the workload is perfectly parallelizable. None of these n things depend on any of the others. So I can easily just divvy them up into n threads and do them independently. However, the problem is when I go to parallelize something, I add overhead. There's overhead involved in starting up threads and tearing them down and joining, whatever. And because of that, even though the work I have is perfectly parallelizable, my result is not what I would expect from just dividing by n. And the way you look at this is you say, before I parallelize, that's the old, I have just some constant T1. That represents the amount of work. It's the big array that I want to do, and it's all perfectly parallelizable. After I parallelize it, Then I'm going to have T1 over N because that is, I'm perfectly parallelizing the work that I had, but I'm also adding this overhead, right? And so my speed up now, remember how the speed up works? It's the old divided by the new. And if I wanted to find P as sort of a parallel fraction, which you could do, right? You could say T1 is the over T1 plus overhead. That would be the parallel fraction. If you wanted to define that constant that way and you do some algebra, then you get something that looks very much like Amdahl's law, but you get a letter P in front of it. You've got a factor P. It's different by a constant factor. And the idea, the thing that I want to impress upon you is that this line here, this middle line, is generic, right? You can apply this to all kinds of situations where Amdahl's law or Gustafson's law might not directly apply. So if you're trying to figure out how much you think you can speed up your code, think about in terms of T old over T new and how to express that mathematically. Is that cool? I think it's cool. All right. The overhead law. All right. Any further questions? All right. How about a quiz? Woohoo! I'm excited to be a part of this plan.